is Afiq bin Abdul Hamid, but on the interwebs I am known as Son of Terra 92. I run a channel on YouTube called Science Epic where I try to communicate science, which is something that I am ultimately very passionate about. That being said, today's presentation will differ a little bit from what was submitted in the report because I will try to be speaking towards the humanitarian and morals and ethics perspective of today's subject. And after hearing some of the feedback that my colleagues and friends received for the report, I decided that I needed to attempt some sort of recovery. So today's presentation will be a bit different, but we'll try to have a lot of fun with it. With that being said, let's begin. Our story begins 100 years ago. Humanity was discovering this new groundbreaking science known as quantum mechanics. And quantum mechanics is the science of the world of the very small, what's inside the atom, and what's inside the atom. We want to understand that, like what is the behavior of the electron. Atoms themselves are actually very wonderfully weird things, because once you think about it, human beings are made out of atoms, and scientists are human beings that try to understand atoms. Essentially, scientists are atoms trying to understand atoms. Mind-blowing stuff. So, quantum mechanics is ultimately gives us a very strange picture of the world of the microscopic. It was so strange that Albert Einstein couldn't really wrap his head around it, even though he had to use it for his own research. There was even a famous quote by Albert Einstein involving God and dice. If anyone can figure this out, anybody knows? First cookie goes out to the person who can figure that out. Albert Einstein says something about quantum mechanics. Anyone? Anybody? Okay, he said that God doesn't play dice with the universe because when you get down to such small levels, you have a lot of uncertainty. You'd think that science involves a lot of exact measurements, but in quantum mechanics you have a lot of uncertainty when you delve deeper and deeper into the world of the very small. While we were making these great discoveries, something was happening in the world that would eventually force our hand in nuclear energy, and that is World War II. Now, World War II was raging across the world, and the Americans were eager to find a way to end it. They were trying to find some sort of game changer. They did this through their R&D project known as the Manhattan Project. And back then it really was a different culture, a different time. You'd have the scientists involved in really being treated like rock stars. They were brought to the best events, they were giving speeches and talks in public. As you can see there, it's one of my favorite scientists. Anyone know who he is? On the left over here, towards the left. That's Richard Feynman. He was one of the scientists in the Manhattan Project. So you have names like Richard Feynman, Edward Teller, and in the middle is J. Robert Oppenheimer, the head scientist that would eventually lead the project to invent the world's first nuclear warhead. And nuclear bomb, actually, warhead is different, but nuclear bomb. And that bomb can be seen on the far side over there. Next question. Anyone know what the name of that bomb was called? Close, close. The cookie is really close now. Yeah, half a cookie. Half a cookie for you. But the name of that bomb is the Little Boy. But for such a little boy, it sure did make quite a big impact. You're so busy. It made quite a big impact on the outcome of the war and the outcome of human history. Now we knew from this moment on that things would never ever be the same. Not never ever getting back together. That's a Taylor Swift song. And one of the principal equations that allowed for this to happen is E equals to mc squared. Wow. One slide, 3 letters, 1 exponent. You'd be thinking, how much can I explain with this? Well, I can actually explain a lot. It marries the contribution of 2 brilliant English scientists. And I'm going to have to drop another question here. For the tele majors, you should know one. And for the mechanical engineering majors, you should know the other. So do we have any telecommunications majors in the house? What? You want to take a guess? You should know this. I'll give you...
Einstein?
No. Einstein discovered this, but it unified the contributions of 2 scientists.
The Maxwell.
Ah, I heard it. Cookie for you, gentlemen.
Another one is Newton. I'm not sure.
That was it. That was correct. It was Isaac Newton. So another cookie for you. Oh, so he's already gotten 2. So
what? Sorry.
One is Newton and is Maxwell.
yes, the 2 were. I was planning on asking you actually because the 2 were James Clerk Maxwell and Isaac Newton. You see, if you were born before the discovery of this equation, you would never think that the physics of electromagnetics and the physics of matter and motion were related. They'd be two different things. On one hand, you have the Maxwell equations, which explains E, and on the other hand, you have the Newton's laws, which explains M and the matter, the stuff that we're made out of. Now, the significance of this equation is that we can figure out that a little bit of matter can be converted to a lot of energy. So you can see that whatever value of M we have, we multiply it by c squared, therefore we have a lot of E. So the next time your friend says that, oh, I don't have the energy to do this or that, just tell them E equals to mc squared. Tell them that they are energy. But I don't suggest you try to make them convert their matter into energy, because I wouldn't want to be near that when it happens. Okay, now it's this conversion of matter into energy that actually gives us nuclear energy. I define nuclear energy as the energy released through either the nuclear fission or the nuclear fusion process for the purpose of generating usable electricity. Now this electricity can be used to power homes, industry, human civilization, like our power grids and such. Now, these two reactions that you can see here are the equations that we have to understand, and I'm going to have to give a short physics demonstration using balls. Yes. Nuclear fission is one of the reactions, and this is so far the only feasible type of nuclear reaction that we can harness for energy. What happens in nuclear fission is that you have a much larger nucleus. As you can see there, we typically use uranium. So it's much larger than the neutron that we eventually shoot at it. So what we're doing in nuclear fission is that we're shooting a neutron at high speed that will eventually split this much larger nucleus into three. And when we split it into three other neutrons, of course there are byproducts, the Ba and Kr over there. So the three neutrons would split from out of the byproduct, and it will eventually hit another uranium, and then the second one will hit another uranium, and the third one will also hit another uranium, causing a chain reaction. And this chain reaction is accompanied by the release of a tremendous amount of energy. And this is the equation that explains our nuclear reactors and explains the bomb that was dropped on Hiroshima. The second type of nuclear reaction is nuclear fusion. This one is a lot less common here on Earth, but it's a lot more common out in
Mars.
Space. Out in space, yes. You see, nuclear fusion is what powers the stars. It's what powers our sun. And what happens in nuclear fusion is the opposite of nuclear fission. Let me get my helium here. Okay, so in nuclear fusion, two smaller nuclei, okay, fuse under very intense pressure and heat, and they produce one much larger helium nucleus. So two small ones make a big one. In the previous one small one splits a big one. Okay, that's the main idea. And the thing is, this is what powers the sun. It gives life to Earth. Without this reaction, we wouldn't be alive. Life wouldn't be possible. Now, that being said, whenever you're looking at the stars, what you're actually seeing is a helium factory. And I'm talking about helium, the noble gas that we put in our balloons, and the gas that if you swallow, it makes you sound like this. I've tried that once. It only lasts for a couple of seconds. So I don't suggest anyone tries large amounts of it. Now, the first one we can do on Earth. The second one we are trying to do on Earth. But like I said, the engineering challenge is in trying to unlock the intense heat and pressure, which we are still trying to master. Next slide.